Hi folks, we're now going to look at some indeterminate forms that are expressed as a power and how we can manipulate them in order to use L'Hopital's rule. So the three examples that you can solve using this method are limits that approach 0 to the infinity, infinity to the 0, and 1 to the infinity. And we'll take a look at this last example here. So we'll take a look at the limit as x approaches 0 from the right of 1 plus sine x to the exponent of cotangent x. And we see that as x approaches 0 from the right, 1 plus sine x approaches 1, and cotangent of x approaches positive infinity. Okay, so let's take a look at how to solve this. Now, not surprisingly, we'd like to get rid of this exponent here, and we'll use a trick that we've seen in the past. So what we're going to do is we're going to define y as being 1 plus sine x to the cotangent of x, and instead of working with y, we're going to work with ln of y, because then allows us to use the ski-slope rule, bring the cotangent of x down, and have it become a multiple. So this will be cotangent of x of ln 1 plus sine x. Okay, so we're now going to work with this limit here. So we'll take the limit as x approaches 0 from the right of ln y, and that's the limit as x approaches 0 from the right of cotangent x times ln of 1 plus sine x. Okay, so now we have something that's of the form infinity times, and as this approaches 1, ln of the expression approaches 0, so 0 times infinity, and we've seen that earlier. So we're going to rewrite this so that it'll fit L'Hopital's rule. And the easiest way to do that is to write cotangent of x as 1 over cotangent of x, which of course is just equal to 1 over tangent of x. So as x approaches 0 from the right, we have ln of 1 plus sine x over tangent of x. And now we have 0 over 0. And so we can apply L'Hopital's rule. So we'll take the derivative of both numerator and denominator. And so for the numerator, we have 1 over 1 plus sine x times the derivative of 1 plus sine x, so cos x, all over the derivative of tangent x, which is just secant squared x. Okay, and this is actually a nice, easy limit to take. I will rewrite this here as cos x over secant squared x times 1 plus sine x. Okay, and we have that the denominator, the secant squared x approaches 1, 1 plus sine x approaches 1, and cosine of x approaches 1. So this limit here is just equal to 1. Now let's keep in mind that what we found is the limit of ln y. In other words, the limit of our, the logarithm of our original expression. So in order to find the limit of 1 plus sine x to the cotangent of x, this is just equal to the limit as x approaches 0 from the right. And here we'll just use the fact that it's e to the ln y, which is what we defined as this expression here. But because the exponential function is just continuous, I think earlier I said we would use the fact that the logarithmic function was continuous, but we're actually using the fact that the exponential function is continuous. And so we know that ln y approaches 1, so this expression will just approach e to the 1, in other words, e. Okay, and we'll take a look at the graph of this function here. Okay, and if we take a look at the graph, we see that as x approaches 0 from the right, this here we're going from 0 to 4, so we can see that that does look like it's just below 3. Okay, so again, this trick will work equally well for any of these three indeterminate forms. So again, our philosophy is always to take the form we have and manipulate it algebraically to turn it into one of the scenarios that L'Hopital's rule deals with.